Hello, my name is Brian Toe, and this is my lab report for the Black Hole Modeling Lab. Within the lab, we modeled a star as it orbited a black hole. This was done to estimate the mass of the black hole, compute its net force, as well as the parallel and perpendicular components of the net force, respectively. The net force was calculated within the model using Newton's second law, in which net force is equal to dp over dt. And so I just broke this down further into how we found it in the lab, including calculating initial momentum and final momentum. And so we plugged that in and found that during the lab. The black hole's mass was estimated using the force of gravity equation, in which the net force equaled the gravitational constant g times the masses of two objects, in this case m1, which is the mass of the star, times m2, the mass of the black hole, and then dividing that by r, which in this case is the magnitude of the star's position squared. And so this can be rearranged to solve for m2, which is the mass of the black hole, and that equals net force times the magnitude of the star's position squared divided by the gravitational constant times the mass of the star. And within the GlowScript code, we plugged in our email to generate a unique trajectory for the star that we used for the position of the star as it moved around the black hole. And we edited the code from line 115 onwards to model this movement around the black hole and to calculate the Fnet components along with mass. So this is the code running as it spits out the mass of the black hole at each point before giving the final mass of the black hole, the magnitude of the net force, the magnitude of the parallel component of the net force, and the magnitude of the perpendicular component of the net force each. And so that's shown here. In terms of the what does it mean question, asking about how net force and rate of change of momentum differing. The rate of change of momentum, dp over dt, is visually seen through the change in motion. However, net force cannot be visually observed and is instead understood to be the cause of momentum changing. According to Newton's second law, the values of Fnet and change in momentum are equal, however. So dp over dt can be used to solve for Fnet, such as what we did in this lab. The what if question regarding if a new black hole was inserted and the motion of the star being unchanged, the new black hole would be of equal mass as it exerts the same force on the star and keeps it on the same path. As such, all of the things used to calculate the mass of the black hole stay the same, and so there's an unnoticeable difference because they're functionally the same. The mass is the same. And so it's impossible to find a mass for the new black hole that differs from the mass of the old black hole because of this. Some possible causes for error in the lab include errors or differences in rounding, which could result in less accurate mass estimations and FNet calculations, as the values used to calculate such measurements are rather large, and even a small rounding error could compound to cause rather large differences in variations in value.